Hey class, welcome back to Electromagnetics. I'm going to continue our look at antennas, and so now that we've defined an antenna, the Hertzian dipole, we now want to look at some parameters that we can use to compare antennas. First, a quick historical background. This person was educated at the University of Munich, the University of Berlin. He went on to work at the University of Kiel and the University of Bonn. Here is a picture of this gentleman, and this is Heinrich Rudolf Hertz. Of course, this is where we get the term Hertz for frequency from in honor of him. So what's notable that he did? Well, he worked in the laboratory, and he built this device here, which is what we call a spark gap. And so you get some kind of source, and you charge it up, and then you close a switch real quick, and it'll cause these to be energized and then create the potential difference here until eventually this will spark. So we call it a spark gap. So this is the schematic of pretty close to what he constructed in the lab. And so, of course, when this switch hits, it energizes these coils, great voltage. And what he found out was when he put a loop, which is the equivalent of a loop antenna, across the lab, when this sparked, he noticed that it produced a potential difference or a voltage across this gap here. And so what he was experiencing was the transmission of an impulse, more so to speak, electromagnetic impulse, which is like an electromagnetic wave, transmitted across the room and inducing voltage in an antenna. So that was pretty monumental in figuring out the concepts of electromagnetic transmission and how we can do it. Again, we're still in part 9, antenna basics, and again we're going to look at radiation, resistance, and directivity today. So to start this, I want to kind of pick up where we left off with these Farfield equations that we introduced last time. Remember, these are the general Farfield, using the Farfield assumptions to simplify our equations for electric and magnetic fields. And so we can use these now to compute the Poynting vector. Remember, we talked about that a couple of sections ago. And that's simply just the E field crossed with the H field. So in this case, it would be E phi, A phi crossed with, or theta, excuse me, crossed with H phi, A phi. And what that results then is a E phi times E theta, excuse me, times H phi times, or in the direction of the resultant radius, which would be these two unit vectors crossed together. So in this case, pulling from the equations above, this would be the result that we would have, is this equation here. So we want to take that now and use it to calculate the total radiated power. And so we're going to assume that this is for a Hertzian dipole, but we're going to assume that it's isometric, that is, it transmits in all directions the same, which is not a totally useless assumption. And so, of course, here we would use spherical coordinates because we'll have the p vector radiating away from the center because our E and H fields are transverse. So they'll be orthogonal to each other and orthogonal to this p direction. So using this differential surface and spherical coordinates, we can set up our integral as such. And so we'll have p dotted with r squared sine theta d phi in the AR direction, going from 0 to pi and 0 to 2 pi. So if we plug in our value from p from a couple of slides back, this is what that integral looks like. And if we were to go through the calculus and evaluate, this is what we would have. And so this is the general equation for the radiated power from our antenna. And again, this is the total radiated power in all directions. So what we want to do now is we want to take the time average of this power, radiated power. And so the only part here And that's what these brackets indicate. And so the only part that really varies with time, of course, is our sinusoidal. But we know from our trigonometric identities that the time average of any sine squared function is going to be equal to 1/2. So this reduces to this equation for our time average radiated power. So now we can strategically rearrange this equation into this. And the reason why we do that is we're trying to see if we can make it in the form of a power equation that we're used to. So this is what we come up with. And so, again, we're trying to make it match the I squared R power equation that we're familiar with. And so in that case, what's in the brackets there is in the placeholder of where resistance would normally reside. So this suggests then that this is an apparent resistance. It's not like you can take an ohm meter necessarily and go and measure this physically somewhere, but this is an apparent resistance that can be associated with the antenna's radiation performance. And we define that generally then as this equation, which is just what's in the brackets up there. And so that's has the unit of ohms. And it's a pretty useful term because this can be used to compare different antennas, because we can calculate this for each different type of antenna. And it gives us one criteria that we look at, which is radiation efficiency. That is, how efficient is it from taking the amount of power we put into it and generating electromagnetic waves. So we can simplify this equation further, because we know that probably 90+% of the time that we're going to be transmitting with an antenna, it'll be in free space. And so our intrinsic impedance we know is going to be 120 pi ohms. So if we plug that in, now our new equation reduces down to this equation. And so this is pretty interesting. This is a constant. So really the only variable here is this dl over lambda. So this would tell us then that this radiation resistance is a function of the electrical length of the antenna. So by electrical length, what I mean is that it's the differential length in terms of lambda, so divided by lambda. So that's what we refer to as electrical length for an antenna, and that's what drives the radiation resistance. Almost like the length of wire in a regular circuit tells us how much resistance is going to be in the wire of that circuit. So this is a pretty important equation. It's used quite a bit, again, in antenna theory. The next aspect we want to consider is that not all, actually hardly any, antennas radiate in a spherical pattern. Most have a non-uniform radiation pattern. And as an example, here's our Hertzian dipole. So if you were to take a meter out here and measure the field, I believe this is the field pattern and this is the radiated power pattern. You measure out here, you're going to measure basically nothing until you swing around here with your meter, and then you'll start to measure here a little bit of field, and then it gets more intense, and then it drops off again as we move around. So it's not in a perfect circle. These vector lines kind of give you a magnitude representation of the field intensity moving around there. So we want to obtain now a metric to characterize this phenomenon, because this has by directivity, what we're saying is what's the ability of the antenna to focus the pattern or focus the signal. We may not want to radiate it all over the place. We may want to just radiate it to another antenna across some length of distance. So we want it to shoot as much of the signal in a certain direction as possible. We want to direct it. And so we can calculate this using both the average power density and the maximum power density. And so we know what our maximum power, radiated power, it's just this equation here, and we maximize the only function of an angle, which is the sine squared theta. So what is the maximum value that sine squared theta could ever be? Well, of course, it's going to be 1. So we can just drop that term out or set it to 1, and this is our equation for maximum radiated power. So now the average power we expressed as this, and by dividing by the 4 pi r squared, which is just a sphere. So that's if we evenly spread it across an entire sphere, what would it be on average? So we can take these two and do the ratio of them of the maximum average power. And when we do that, directivity is what we come up with. So that directivity is defined as the maximum. So in whatever direction the maximum is, what that maximum radiated power is divided by the average over the whole sphere. And so for the Hertzian dipole, we have expressions for this already that we've derived, pulling from previous slides. This is our maximum and this is our average. So you can see a lot of things are going to divide out. Basically, usually I think with 16 over 24, which is 1.5. So the directivity of a Hertzian dipole is 1.5. So the definition for directivity can be generalized for any type of antenna in the terms of the power density radiation pattern. So if someone gives us a function for the radiated power, that is, if as I start to go in every theta and phi direction, it'll plot out, what that power is. We can just find the maximum value of that, and then we can integrate it over this integral. And so that's the general form. So if we're given this equation for this, then we can calculate the directivity. And so again, this allows us to calculate that for any antenna that we are given, or if we can obtain that function as well, you can do it in the lab and measure it out and come up with your own function to figure this out. So again, just like radiation resistance, this is another very important and widely used criteria to characterize antennas and compare antennas. If you're wanting an antenna for like a radio station, well, you want very low directivity. You want it to broadcast the same signal strength in all directions. But if you're using this for like a cell tower or a microwave antenna where you're transmitting between stations, directly between them, and you don't want to broadcast it everywhere, then this would be you'd want a very high directivity. So you don't want 1 or 1.5, you want 10 or 100 or something like that if possible. So as an example, let's compute the directivity corresponding to the power density function given by this, sine squared theta cosine squared theta. So we have an antenna that this is the definition of the radiated power pattern. So if we do that, we need to take the maximum of what this would be over the integral of this here, which would just be sine squared theta cosine squared times sine theta d phi. So that's why it's sine cubed. And so we can use some trigonometric identities and then just common calculus. And when we do, we come up with that this is 1/4 sine squared 2 theta max over the integral of sine cubed theta minus sine to the 5th theta. And when we evaluate all this, again, it's just a calculus problem. We'll come up with 1 7/8. So that would be the directivity. So we know that our Hertzian dipole was 1.5. So this is 1 7/8. So this is slightly more directive in its pattern. Not tremendously more, but it is slightly more than just a Hertzian dipole. So if you were to work in the field of antennas, you can find these tables and actually way more than this. This is just a sample page of some of the characteristic things that you can calculate for antennas to compare them. Most of these are short dipoles. So you can have the length of L, short dipole where L is lambda over 10, with average current of I is 0. Same thing with an average current, exciting current of half I0. Linear lambda over 2 dipole with sinusoidal current distribution, a small loop single turn of any shape, so on and so forth. So first column here, you see we can calculate the radiation resistance. So like these two, for instance, this short dipole lambda over 10 is much more efficient in translating the source power into a transmitted electromagnetic wave than this linear lambda over 2 is. It has a radiation resistance of 73. There's some other characteristics here we're not going to look at. We want to mainly see this last column, the directivity. So this first row is isotropic, and so that's not a real life per se antenna. That's more of a theoretical model. So directivity of 1, so that's giving us the sphere radiating equally in all directions. But you really can't realize that in real life, at least not effectively. So we can look at these others. Most of these have the same directivity, 3 over 2. When we get down to this linear lambda over 2, it's 1.64. So it's a little more directive than these other ones. So just wanted you to see that. So you might see these kind of tables, if you get out and work with antennas in your career.